Every detail in this story comes from real scientific research and observation. Something passed through your body tonight? You did not feel it. It traveled at the speed of light, through the vacuum of space, through the rock beneath every city on Earth, through the ocean floors, through the atmosphere, through the walls of every building, through every human body on the planet, and continued outward, undisturbed, into the dark beyond. It was not light. It was not sound. It was not radiation. It was a distortion in the shape of space itself. 1.3 billion years ago, two objects collided in the dark, objects so massive that each one contained more compressed matter than 30 suns. They had been circling each other for millions of years, a slow, tightening spiral, losing energy with every orbit, drawing closer by a fraction of a millimeter per revolution. The spiral was patient. It had time. It had billions of years. And then, in the final fraction of a second, everything ended. In 0.2 seconds, they merged. In 0.2 seconds, a mass equal to 3 entire suns was converted, not into heat, not into light, into a ripple, a single ripple in the geometry of space-time itself. And in that moment, the power released exceeded the combined light output of every star in the observable universe. The universe did not announce this. No flash, no explosion visible from a distance. Just a wave moving outward in every direction at the speed of light, distorting the shape of space as it traveled. It traveled for 1.3 billion years. It passed through galaxy clusters, through the empty spaces between galaxies where almost nothing exists, through the outer arms of our own Milky Way, through the quiet reaches of our solar system, through the orbit of Jupiter, of Mars, of Earth. And on September 14th, 2015, at 5:51 in the morning, Eastern Time, it arrived. A laser in Louisiana flickered, not because something hit it, because the space the laser was traveling through, the space inside a 4-kilometer vacuum tube, briefly changed shape. The same laser flickered in Washington state exactly 7 milliseconds later. The distortion they recorded was real. It was also almost incomprehensibly small, smaller than 1,000th the diameter of a single proton. The most precise measurement in the history of science had just detected the most violent event in the observable universe, and it registered as something smaller than the nucleus of an atom. For 40 years, scientists had been building toward this moment. Decades of failed funding proposals, of instruments too noisy, of skeptics who said the signal would never come. The machine they built, 2 L-shaped detectors, each arm 4 kilometers long, bouncing laser light 280 times before it reached a detector, was so sensitive that trucks on the highway outside could contaminate the data. Trains 2 kilometers away could contaminate the data. The ocean waves crashing on the Gulf Coast could contaminate the data. The machine had to be quieter than the quantum mechanical noise of space itself. And when the signal finally came, no one was watching. The detectors had been running in engineering mode for only a few days after a major upgrade. A graduate student in Hanover, Germany, noticed something unusual in an automated data stream at a few minutes after noon, local time. He flagged it. No one was certain it was real. It would take 5 months of verification before anyone dared to believe it. 5 months of sitting with what might be the most important detection in the history of astronomy. and not being sure, and then they were sure, and then the universe was never the same. Tonight, you are going to understand what that signal was, where it came from, how it was built, how it traveled, how it was caught, and what it means that we can now hear things the universe has been saying since before the Earth existed. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. For a century, the distortion of space was a mathematical prediction. Albert Einstein published his general theory of relativity in 1915 and immediately recognized that his own equations implied something strange, that accelerating masses should produce waves in the fabric of spacetime, ripples moving outward at the speed of light. He wrote about it. He also doubted it. He suspected the effect would be so small that it could never be measured and wondered whether it was physically real or merely a coordinate artifact. He was right about the measurement problem. He was wrong about the physics. The waves are real. They have been traveling through the universe for as long as massive objects have been accelerating, and on a September morning in 2015, a machine made of mirrors and laser light proved it. Tonight, you are going to experience that proof from the inside. You are going to begin with the fabric itself, what spacetime actually is, what it means for it to bend, and what it means for that bending to move. Then you will travel back to the source, two black holes, circling in the dark, losing energy with every orbit, spiraling toward a collision that released more power in a fraction of a second than anything in the observable universe had released before or since. Then you are going to stand inside the machine. Now imagine you are standing very still. You are not in a building. You are not indoors. You are standing in open space, not the vacuum of outer space, but a wide, flat, still landscape at night. The ground beneath your feet is firm. The air is quiet. There are no lights nearby. The sky above you is full of stars. You are going to stand here for a moment, and you are going to think about what the ground beneath your feet actually is. Not rock, not soil, not atoms compressed into a solid form. All of that is true, but beneath all of it, beneath the chemistry and the geology and the physics of matter, is something more fundamental. The ground beneath your feet occupies space. It exists inside a geometry. And that geometry, the shape of the space around you, the rate at which time passes through this location, is not fixed. It is not a backdrop. It is not a container that sits unchanged while events happen inside it. It curves, it flexes, and tonight it is moving. Einstein's insight in 1915 was not simply that gravity bends light or that massive objects slow time, though both of those things are true and have been confirmed by countless experiments. His deeper insight was structural, that what we call gravity is not a force transmitted between objects through empty space. It is the geometry of space-time itself responding to the presence of mass and energy. A massive object does not pull on other objects from a distance. It reshapes the geometry around itself, and other objects follow the curves in that geometry, the way a ball rolls along the surface of a curved sheet. This is not a metaphor. The rubber sheet that teachers use to demonstrate gravity, a heavy ball sitting in a stretched membrane, causing smaller balls to roll toward it, is a useful picture, but it is incomplete. The real thing is four-dimensional. It includes not just the three spatial dimensions you can point to, but time itself. The presence of mass does not just curve the space around an object. It curves the spacetime, which means it affects both the paths objects travel through space and the rate at which time passes for them. The closer you are to a massive object, the more slowly time passes for you. This is not a philosophical statement. It is a measured fact. GPS satellites in orbit must correct for this effect continuously. Their clocks run faster than clocks on the ground because they are farther from Earth's center of mass. If engineers did not account for this, GPS positioning would drift by approximately 11 kilometers per day. You are standing on the surface of Earth, close to its center of mass, and time is passing for you more slowly than it would if you were floating in deep space. The difference is small, about 1 part in 700 million per day, but it is real. The ground beneath your feet is a location in curved spacetime, and the curvature is caused by the mass of the planet beneath you. Now hold that thought and take one step further. If gravity is geometry, if the curvature of spacetime is what we feel as weight, as the tendency of objects to fall, then what happens when that geometry changes? What happens when mass moves? A stationary mass curves the spacetime around it into a stable shape, but an accelerating mass, an object that is speeding up, slowing down, or changing direction, does not just reshape its local geometry, it sends that change outward. The disturbance propagates through space-time the way a disturbance in water propagates as a wave across the surface. This is a gravitational wave. Not a wave of gravity in the sense of varying gravitational pull, a wave in the geometry of space-time itself. As the wave passes through a region of space, it alternately stretches that region in one direction and compresses it in the perpendicular direction. Then it reverses, stretch, compress, reverse. The oscillation is transverse. The distortion is perpendicular to the direction the wave is traveling, the same orientation as a wave on a string. If a gravitational wave were passing through this room right now, and statistically one probably is, the space between 2 points in one direction would be slightly longer than normal, while the space between 2 points at 90 degrees would be slightly shorter than the opposite. The room itself would be breathing very slowly by an amount too small to ever measure without instruments of extraordinary precision. The quantity that describes the size of this stretching and compressing is called strain, represented by the letter H. Strain is defined as the change in length divided by the original length. A strain of 1 would mean a 1 meter ruler had become 2 meters long. A strain of 1,000th would mean that same ruler had grown by 1 millimeter. The strain of the gravitational wave detected on September 14, 2015, was approximately 10 to the negative 21. That is not 1,000th, that is 1,000th of 1 billionth of 1 billionth. Written as a decimal, it is a 0, then a decimal point, then 20 zeros, then a 1. To put this in physical terms, at that strain, a ruler 4 kilometers long would change in length by less than 1,000th the diameter of a proton. A proton is approximately a femtometer across, 10 to the negative 15 meters. 1,000th of that is 10 to the negative 18 meters. The arm of LIGO changed in length by less than that. This is what the machine had to detect. Stand in the still night air for a moment and let that number settle. The signal that carried the record of 2 colliding black holes, an event that released more energy than all the stars in the visible universe combined, arrived at Earth as a distortion smaller than the nucleus of an atom. This is not a failure of the signal. This is a consequence of the extraordinary stiffness of spacetime. Spacetime is not soft. It is not elastic in any ordinary sense. It resists deformation with an intensity that makes steel seem like water. To produce even this tiny ripple at the distance of 1.3 billion light-years required a mass equivalent to 3 entire suns to be converted directly into gravitational wave energy in less than a quarter of a second. The universe spent 3 solar masses to send us a whisper. Gravitational waves propagate at exactly the speed of light. This was confirmed by GW 170817, a neutron star merger detected in 2017, which arrived simultaneously with a gamma-ray burst observed by the Fermi Space Telescope. The time difference between the gravitational wave arrival and the gamma-ray signal was 1.7 seconds, an insignificant delay likely caused by the gamma rays having to travel through the ejected material of the merger before escaping freely into space. The gravitational wave and the light had been traveling for 130 million years, and they arrived within 1.7 seconds of each other. The speed of gravitational waves differs from the speed of light by less than 1 part in 10 to the 15th. They travel at the same speed because they are both fundamental features of the same underlying structure, spacetime, rather than things that travel through spacetime. Light is a wave in the electromagnetic field, which is embedded in spacetime. Gravitational waves are waves in spacetime itself. Both propagate at the characteristic speed that the geometry of the universe assigns to all massless disturbances. You feel the night air against your skin. The temperature at this location in space has not changed. The chemistry of the atmosphere is unchanged. The geological composition of the ground is unchanged. And yet, right now, a gravitational wave is passing through everything you can see and touch. It entered the planet on one side, and it is exiting from the other. It is passing through the iron core of the Earth as easily as it passes through air. Nothing stops it, nothing absorbs it, nothing slows it by a measurable amount. This is another defining property of gravitational waves. They interact extraordinarily weakly with matter. This is both what makes them so difficult to detect and what makes them so scientifically valuable. Light can be blocked, absorbed, scattered, redshifted by dust, and obscured by bright foreground objects. Gravitational waves pass through everything. They carry information about their source in a form that nothing in the universe between the source and the detector can alter. When a gravitational wave arrives at a detector, it is carrying information about exactly what happened at the source, unfiltered, unscattered, unchanged, even if the source was surrounded by gas, dust, or the debris of an explosion. For most of astronomical history, everything we knew about the universe came from light in various forms: visible light, radio waves, X-rays, gamma rays, infrared, all of it electromagnetic radiation, all of it subject to the same limitations. It can be blocked. It cannot escape from inside a black hole event horizon. It is emitted by charged particles and therefore tells us primarily about the electromagnetic behavior of objects. Gravitational waves tell us about mass and motion directly. They carry a different kind of information. They reach us from places where no light can escape. They tell us about events that produce no significant electromagnetic signal at all, such as the merger of two black holes. Before 2015, No one had ever directly detected a gravitational wave. The universe had been producing them continuously, from black holes merging, from neutron stars spiraling together, from supernovae, from the first fractions of a second after the Big Bang itself. For the entire history of astronomy, for every night any human being had ever spent looking at the sky, this information had been passing through us and through every instrument we built, undetected. We had only one sense with which to study the cosmos. On September 14th, 2015, we developed a second one. The air around you is very still now. The stars above are very bright. You know, standing here, that the light from the nearest of those stars left its surface years ago. The light from the most distant ones left before the Earth existed. And passing through all of it, through the light and between the light and beneath the light, are waves in the geometry of the universe itself, carrying news from events so violent they strain the boundary of what physics allows. Your breathing is slow. Your weight on the ground is a consequence of curved spacetime. The fact that time is passing at all is a feature of the same geometry, and the signal that LIGO detected, the one that proved all of this, is not merely mathematical, is part of a continuous stream that the universe has been broadcasting since its earliest moments. Let yourself rest in that. The ground is steady. The sky is deep. In, out. We will go further now. Before we travel to the source itself, it is worth pausing on something that happened long before the machine was built, because the machine did not emerge from nothing. It was built on a foundation of indirect evidence. Evidence so compelling that by the time LIGO first turned on, most physicists were not asking whether gravitational waves existed. They were asking when LIGO would be sensitive enough to find them. The evidence came from pulsars. A pulsar is a neutron star, the collapsed remnant of a massive star, spinning rapidly and emitting a narrow beam of radio waves from its magnetic poles. As the star rotates, this beam sweeps across the sky like the light from a lighthouse, and if Earth happens to be in the path of the beam, we receive a pulse of radio energy with every rotation. Some pulsars spin hundreds of times per second. Their pulses arrive with the reliability of an atomic clock, so reliably that anomalies in pulse arrival times can be used to infer things about the environment the pulses are traveling through. In 1974, two astronomers, Russell Hulse and Joseph Taylor, working at the Arecibo Observatory in Puerto Rico, discovered a pulsar that was unusual. It was a millisecond pulsar, spinning approximately 17 times per second, and it was in a binary system with another neutron star. The two neutron stars were orbiting each other with a period of approximately 7.75 hours. Hulse and Taylor named it PSR B1913 plus 16. The binary pulsar was immediately recognized as a potential test of general relativity. If the two neutron stars were orbiting each other, and if general relativity was correct, they should be emitting gravitational waves. And if they were emitting gravitational waves, they should be losing orbital energy. And if they were losing orbital energy, the orbital period should be decreasing. The two stars should be slowly spiraling inward, completing each orbit in slightly less time each year. Hulse and Taylor measured the orbital period over several years, then over more than a decade, then over 2 decades. The orbital period was decreasing. The rate of decrease matched the prediction of general relativity, the rate of energy loss from gravitational wave emission, to within a fraction of a percent. The agreement was not approximate, it was precise, comprehensive, and confirmed by continued observation over more than 40 years. This was the first indirect detection of gravitational waves, not a direct measurement of space-time rippling that would not come for another 40 years, but a measurement of the energy loss from a binary system that could only be explained by gravitational wave emission. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. When LIGO was being designed, the Hulse-Taylor binary pulsar was the evidence physicists cited when asked whether the investment was justified. The waves existed, general relativity had already predicted them, and the prediction had already been confirmed. The question was only whether human ingenuity was sufficient to build an instrument capable of detecting the waves directly at the distance of astrophysically interesting sources. The question turned out to have a yes. 1.3 billion years ago, before the first complex animal life appeared on Earth, before the Cambrian explosion, before the first vertebrates, before the continents had arranged themselves into anything resembling their current positions, in a galaxy whose name we do not know, in a region of space 1.3 billion light-years from where Earth would eventually form, two stars reached the end of their lives. They were massive stars. Astronomers classify stars by their mass relative to the Sun, and these two were in the range of roughly 50 to 80 solar masses each during their main sequence lifetimes, the period when a star fuses hydrogen into helium in its core. Stars this massive live quickly and die violently. Where the Sun will spend approximately 10 billion years on the main sequence, a star of 50 solar masses spends only a few million years before exhausting its hydrogen fuel. The more massive a star, the faster it burns. When a massive star exhausts its core hydrogen, it begins fusing heavier elements, helium into carbon, carbon into oxygen, oxygen into neon, neon into silicon, silicon into iron. Each fusion stage is faster than the last. The silicon to iron phase takes approximately 1 day. When an iron core forms, fusion stops entirely. Iron is the end of the line. Iron fusion does not release energy, it consumes it. The core, no longer supported by outward pressure from fusion, collapses in less than a second. The collapse is halted when nuclear density is reached, the point at which neutrons resist further compression, and the resulting shock wave blows the outer layers of the star into space in a supernova explosion. What remains at the center depends on the mass of the collapsing core. For a core below approximately 3 solar masses, the result is a neutron star, an object roughly 20 kilometers across, composed almost entirely of neutrons packed together at nuclear density, spinning rapidly and radiating energy as a pulsar. For a core above approximately 3 solar masses, not even the resistance of neutron degeneracy pressure is sufficient. The collapse continues past neutron star density. Gravity wins completely. The matter compresses into a singularity, a point of infinite density, and a region of spacetime forms from which nothing, not even light, can escape. A black hole. Each of the 2 stars in this system underwent this process. Each produced a black hole. The first black hole had a mass of approximately 36 solar masses. The second had a mass of approximately 29 solar masses. These masses were inferred from the gravitational wave signal they eventually produced, from the frequency and rate of change of the waveform, which encodes the chirp mass of the system directly, through equations derived from general relativity. but that detection was 1.3 billion years away. At this moment in time, the two black holes were simply there, in orbit around each other, as their parent stars had been before them. Binary star systems are common. Approximately half of all Sun-like stars exist in binary or higher-order multiple systems. For very massive stars, the fraction may be higher. The two progenitor stars had orbited each other during their lifetimes, and when they died, their black hole remnants continued to orbit. The orbit was wide at first. The two black holes circled each other at a distance of hundreds of solar radii, completing each orbit over a period that may have been days or weeks. And at each orbit, something happened that ordinary Newtonian gravity does not predict. They lost energy. In Newtonian mechanics, two objects orbiting each other in a vacuum would continue orbiting forever. There is no friction, there is no drag. The orbit is stable indefinitely, but Newtonian mechanics does not account for general relativity, and general relativity changes the picture fundamentally. Two massive objects in mutual orbit are accelerating, continuously changing their velocity vectors as they follow their curved paths. Accelerating masses emit gravitational waves, and gravitational waves carry energy. The energy has to come from somewhere. It comes from the orbital energy of the system. As the binary black hole system radiates gravitational waves, it loses orbital energy. As it loses orbital energy, the two black holes move closer together. As they move closer together, their orbital velocity increases. They complete each orbit faster. As their orbital velocity increases, they accelerate more strongly, and they emit gravitational waves more intensely. The process feeds on itself, the in-spiral accelerates. The frequency of the gravitational waves they produce increases as the orbit tightens. This is the chirp. The waveform of a binary merger is not a single tone, it is a frequency sweep, starting low and slow, rising in both frequency and amplitude as the objects spiral inward, reaching a peak at the moment of merger, then abruptly transitioning to the ring down as the merged object settles. Physicists call this the chirp because, rendered as sound by shifting the gravitational wave frequencies into the audible range, it sounds remarkably like the call of a small bird. A brief rising tone, followed by silence, hundreds of millions of years of in-spiral compressed into a fraction of a second of audio. The in-spiral of the GW150914 system was not brief. The two black holes spent an extraordinary length of time in this slow orbital decay. Early in the process, when the orbit was wide, the energy loss per orbit was tiny, and the decay was imperceptibly slow. Millions of years passed with almost no change in the orbital parameters. Then tens of millions, then hundreds of millions. The universe around the black holes was not static during this time. Galaxies were forming and evolving. Stars were being born and dying across the cosmos. On a planet forming far away, simple single-celled life was slowly developing toward complexity. But the two black holes circled on. The orbit was tightening, 1/fraction of a millimeter per revolution at first, then faster. The mathematics of this orbital decay was worked out in detail by Peter Peters in 1964, a graduate student working under Richard Feynman at Caltech. Peters derived an expression for the rate at which a binary system loses orbital energy to gravitational wave emission, and from this derived a formula for how long any given binary system would take to merge from its initial separation. The formula is called the Peters formula, and it is one of the foundational equations of gravitational wave astronomy. Applied to the GW1 50914 system, two black holes of 36 and 29 solar masses initially formed in stellar collapse. The Peters formula gives an in-spiral timescale on the order of billions of years for wide initial separations. Consistent with the evolutionary picture, the system formed long ago and spent most of its history in the slow early phase of orbital decay, where the signal was far too low in frequency for any ground-based detector to reach. The quantity that most directly encodes the binary's masses in the gravitational wave signal is called the chirp mass. It is a specific combination of the two component masses, the 1/5 power of the product of the individual masses cubed, divided by the 1/5 power of the total mass squared. This unusual combination emerges naturally from the equations governing gravitational wave emission. It is the quantity that determines how rapidly the orbital frequency evolves, and it can be measured directly from the rate of change of the gravitational wave frequency in the chirp signal. No other information about the system is needed. For GW 150914, the chirp mass was approximately 28.3 solar masses. From this single number, measured precisely from the waveform, the orbital evolution was fully determined. Combined with the total mass, inferred from the merger frequency and the ringdown, the individual component masses could be extracted with uncertainties of a few solar masses. The in-spiral waveform also encodes the spins of the individual black holes, though with more ambiguity and larger uncertainties. Black hole spin affects the precession of the orbital plane and introduces subtle modulations in the waveform amplitude and phase. For GW 150914, the component spins were not well constrained by the data. The signal was short and the in-spiral phase contained relatively few cycles in the LIGO band. Later detections involving lower mass systems that spent more time in the detector band before merging would provide much tighter constraints on component spins. Then faster. The gravitational wave frequency, which is exactly twice the orbital frequency of the binary system, was increasing, but for most of this billion-year span, the frequency was so low that no instrument in existence could have detected it. In the millihertz range, then the sub-millihertz range. The waves pass through the universe at the speed of light, radiating outward in every direction, carrying the imprint of the slow in spiral, but too low in frequency to be detected by LIGO, which is sensitive only to frequencies above approximately 10 Hz. The signal only entered LIGO's detection band in the final seconds. You are standing in the space near these two black holes now, not close. Nothing about close is survivable here, but at a distance where the geometry of space is noticeably disturbed. You can measure the distance to the closer black hole, and then measure it again a fraction of a second later, and find that the distance has changed. Not because you moved, because the space between you and it stretched and compressed as the binary orbit progressed. The effect oscillates at twice the orbital frequency. When the orbit takes days, the oscillation in local space-time geometry takes days. When the orbit tightens to seconds, the oscillation takes seconds. You can feel at this distance the rhythm of the orbit and the geometry of the space you occupy. It is not something your body detects, but a precise enough instrument could register it. The final minutes begin. When the two black holes are separated by a distance roughly comparable to their own sizes, the in-spiral enters its terminal phase. At this point, the gravitational wave emission is intense, and the orbital evolution is rapid. The two objects are moving at a significant fraction of the speed of light. Their orbital period has shrunk to fractions of a second. Relativistic effects are dominant. The inspiral is no longer a slow Newtonian spiral modified by small corrections. It is a fully relativistic plunge. For GW150914, the last few orbits took place at velocities approaching 60% of the speed of light. The separation between the two black holes at merger was approximately 350 kilometers, less than the diameter of Iceland. Objects with a combined mass of 65 solar masses, separated by 350 kilometers, orbiting each other at 60% of light speed. In the final 0.2 seconds, the two event horizons, the boundaries from which nothing escapes, touched and merged into a single, larger event horizon. The spacetime geometry in the immediate vicinity of the merger was violently, catastrophically distorted. The resulting object was not immediately a clean, stable black hole. It was a rapidly rotating asymmetric object, ringing with perturbations, a Kerr black hole that had not yet settled into its final configuration. It radiated away this asymmetry as gravitational waves. This is the ringdown. The ringdown is a damped oscillation, space-time ringing at specific frequencies determined by the mass and spin of the final black hole, losing energy with each cycle, settling toward the stable Kerr geometry over milliseconds. The ringdown frequencies are called quasi-normal modes. They are the fingerprint of the final black hole. They encode its mass and angular momentum directly in the waveform. Measuring the ringdown allows physicists to confirm that the final object is consistent with the predictions of general relativity for a Kerr black hole. This has been done for GW150914, and the results are consistent with a final black hole of approximately 62 solar masses, spinning at roughly 2/3 of the maximum possible spin rate. The remaining mass, 3 solar masses, was emitted as gravitational waves. 3 solar masses, the mass of 3 stars like the Sun, converted entirely into ripples in space-time geometry. Not into heat, not into light, not into kinetic energy. Into the fabric of space itself, propagating outward at light speed in every direction from the merger site. The peak power output of this emission was approximately 3.6 times 10 to the 49 watts. The Sun's luminosity, its total power output in all forms, is approximately 3.8 times 10 to the 26 watts. The peak gravitational wave power of GW150914 exceeded the luminosity of the Sun by a factor of roughly 10 to the 23, 100,000 billion times the total power output of the Sun. And the combined light output of all the stars in the observable universe is estimated at roughly 10 to the 49 watts as well, placing the peak gravitational wave power of this merger in the same order of magnitude as the total electromagnetic luminosity of the entire observable universe. For those 0.2 seconds, a single event in a single galaxy produced as much power in gravitational waves as every star in the observable universe produced in light. And it arrived at Earth as a distortion smaller than a proton. The wave expands now, outward in every direction from the merger site, moving at light speed, carrying the chirp waveform, the slow, low-frequency rise of the inspiral, the sharp, high-frequency sweep of the plunge, the brief damped oscillation of the ringdown. The amplitude decreases as it travels, proportional to the inverse of the distance. At 10 times the distance, the strain is 10 times smaller. At 100 times the distance, 100 times smaller. At the source distance, the strain is an enormous reduction from its original amplitude, scaled by the inverse of its travel distance. The wave is moving through the universe. It has been moving for 1,000,000 years when the Cambrian explosion begins on Earth, the sudden diversification of animal body plans in the fossil record at approximately 538 million years ago. The wave has not yet covered half its journey. It passes through the accumulated stars and gas of countless galaxies, through voids between galaxy clusters where the density of matter is less than 1 atom per cubic meter, regions so empty they make the best vacuum achievable on Earth seem dense by comparison. It continues. It reaches the outer boundary of the Milky Way, while the first anatomically modern humans are beginning to spread across Africa. It enters the disk of the galaxy, crossing the spiral arms, moving through the thin diffuse interstellar medium between star systems. At light speed, crossing the Milky Way's 100,000 light-year diameter takes 100,000 years. It approaches our solar system while the last ice age is receding and human agriculture is beginning to develop. It passes the orbit of Neptune, then Uranus, then Saturn, then Jupiter. It moves at light speed through the inner solar system. It reaches Earth. Specifically, it reaches the Louisiana Gulf Coast at 4:51 a.m. local time, 9:51 a.m. Greenwich Mean Time on September 14, 2015. The LIGO detector at Livingston, Louisiana is waiting. Not watching, not alert, running in automated engineering mode, its data being recorded by pipeline software, its output being processed by algorithms, looking for coincidences and signals. No human being was sitting at a console watching the data stream when the wave arrived. The wave passed through the detector anyway. In the 4-kilometer north arm of the interferometer, the spacetime geometry briefly stretched. In the 4-kilometer east arm, it simultaneously compressed. The length difference between the arms, which is what the interferometer measures, changed by a distance equivalent to less than 1,000th the diameter of a proton. The laser light traveling inside the detector registered this change as a phase shift. The phase shift produced a change in the output power of the interferometer. The change in output power was recorded by the data acquisition system. Exactly 7 milliseconds later, the wave reached Hanford, Washington. The second LIGO detector recorded the same characteristic waveform, the chirp shape of the in-spiral, merger, and ring down of a binary black hole system, delayed by exactly the time it takes light and gravitational waves to travel from Louisiana to Washington. The signal lasted approximately 0.2 seconds in the detector band. The total duration of the in-spiral phase visible in the detector, above 10 Hz, the low-frequency cutoff of advanced LIGO, was approximately 0.45 seconds. The merger happened at the peak frequency of approximately 150 Hz. The ring down decayed over the following milliseconds. What the detector had recorded, though no one knew it yet in those first minutes, was the very first direct detection of a gravitational wave in human history. The first detection of a binary black hole merger. The first direct evidence that black hole binaries exist. And the loudest, most significant scientific announcement that would be made in the field of astrophysics in decades. But the data was just sitting there in a pipeline. Outside, in the Louisiana bayou, Birds were beginning to call. The sky was lightening. The detector hummed in its concrete housing, surrounded by active seismic isolation systems, cooled to reduce thermal noise, its laser bouncing between mirrors polished to atomic scale smoothness. It had done its job. It had detected a signal from 1.3 billion years ago, from a collision more violent than anything in the observable universe since the Big Bang. It had caught the chirp, and the universe continued on, exactly as before, indifferent to whether anyone noticed. Somewhere above you, the sky is lightening or dark, depending on where you are and what time it is. The geometry of the space around your body is curved by Earth's mass. Time is passing for you at a rate slightly slower than it would in deep space. A gravitational wave, probably from some stellar mass binary system somewhere in our galaxy or beyond, is likely passing through you right now, moving at the speed of light, imprinting no detectable mark on your body as it goes. You are immersed in a universe that speaks continuously in the language of bent space. You are lying still. Your breathing is slow and even. The thoughts that were circling earlier in the day, the things that needed doing, the conversations still unfinished, they are quieter now. They don't require anything from you in this moment. The wave has already arrived. It passed through Earth on a September morning and kept moving. It is currently 8 light years beyond Earth, somewhere in the vicinity of the nearby star system of Sirius, still moving outward at light speed, still carrying the exact waveform of the in-spiral and merger of those two black holes, now barely detectable against the background noise of the universe, diminished by the inverse of an ever-growing distance. In 1 billion years, it will still be moving. In 10 billion years, it will still be moving. It will outlast the sun. It will outlast the Milky Way's current form. It will propagate outward, carrying its information until the universe is too cold and too dark for anything to receive it. But we received it. In this narrow window of time, on this particular morning, with instruments we had spent 40 years learning how to build, we were listening. And the universe spoke. Let that be the last thought as you rest now. The signal was real, the waves are real, the curved, breathing, rippling geometry of space itself is real, and it is present everywhere you will ever stand, or lie, or sleep. In, out, you are resting inside the fabric of space-time. It holds you exactly as it holds every star, every galaxy, every black hole in the observable universe, by geometry, by curvature, by the patient mathematics of a universe that has been solving its own equations since before the first atom existed. Sleep is close now. The science has settled around you like a weight that is not heavy, like a depth that is not cold. The two black holes merged 1.3 billion years ago. The wave has already arrived. There is nothing left to wait for. Let the rest of the script carry you. Let the sound of the narration become background, then texture, then nothing. You are in the universe. You are made of matter that was forged in the cores of stars. You are held in place by curved space-time. And you are, right now, the thing in the universe that noticed. That is enough. Rest now. You are standing inside a tube. It is 4 kilometers long. The tube is made of steel, sealed and evacuated to a pressure lower than the surface of the moon. The air inside has been removed so completely that it contains fewer molecules per cubic centimeter than the best natural vacuum in the solar system. The tube runs in a straight line across the Louisiana Bayou, across the flat, humid lowland south of Baton Rouge, through terrain that floods seasonally and hums with insect life in summer, and for the entire 4 kilometers of its length, nothing moves. Nothing is allowed to move. At the end of the tube, there is a mirror. The mirror is 25 centimeters across. It is made of fused silica, a form of glass with an extremely low mechanical loss, meaning it dissipates almost no energy when it vibrates. Its surface has been polished to a smoothness of less than 1 angstrom, 1/10,000,000th of a meter, across its entire face. At this level of smoothness, the mirror reflects approximately 99.9995% of all incident laser light. The remaining 0.0005%, 5 parts per million, passes through. The mirror is, by any measure, among the most precisely manufactured objects in human history. There is a second mirror at the other end of the tube. Between them, a laser beam bounces. Not once, not twice. The laser light is trapped between these 2 mirrors. The tube is configured as a Fabry-Perot cavity, and the beam makes approximately 280 round trips before it finally exits. At the speed of light, 280 traversals of an 8-kilometer round trip, 4 kilometers down, 4 kilometers back, means the effective optical path length of each arm is approximately 1,120 kilometers. The detector is measuring the difference in length between 2 4-kilometer tubes, but the laser light experiences those tubes as though they were 1,120 kilometers long. This optical path multiplication is one of the central engineering achievements that makes detection possible at all. The machine you are standing inside is called LIGO, the Laser Interferometer Gravitational Wave Observatory. There are 2 of them, this one in Livingston, Louisiana, and an identical one in Hanford, Washington, approximately 3,000 kilometers to the northwest. They are L-shaped. Each L has 2 arms, oriented at 90 degrees to each other, each arm 4 kilometers long. The fundamental measurement the interferometer makes is simple in principle. It compares the length of one arm to the length of the other. If the 2 arms are exactly the same length, the laser light returning from both arms arrives at the detector in phase. The peaks and troughs of the 2 beams align, and the output is dark. If one arm is even fractionally longer than the other, the returning beams are slightly out of phase, and the output brightens in proportion to the mismatch. A gravitational wave passing through the detector would stretch one arm and compress the other simultaneously. This is exactly what an interferometer is built to detect. The mismatch would appear as a transient brightening of the output, a signal that rises and falls with the frequency and amplitude of the passing wave. In principle, this is straightforward. In practice, everything in the physical world conspires against it. The problem is not the concept. The problem is scale. The strain of a detectable gravitational wave is approximately 10 to the negative 21. For a 4-kilometer arm, this corresponds to a length change of approximately 4 times 10 to the negative 18 meters. This is a distance roughly 1,000 times smaller than the diameter of a proton. The laser light traveling inside the interferometer must be sensitive to a path length change of this magnitude, while the entire physical structure of the detector is subject to seismic vibration, thermal noise, acoustic disturbance, laser power fluctuations, and the irreducible quantum noise of the photons themselves. Seismic noise alone would overwhelm the signal by many orders of magnitude without mitigation. The ground moves constantly, not earthquake-scale movement, ordinary microseismic motion caused by ocean waves interacting with the seafloor hundreds of kilometers away. This motion is transmitted through bedrock at low frequencies, and it shakes the mirrors of the interferometer. Unmitigated, the seismic displacement of the mirrors is billions of times larger than the gravitational wave signal. The solution is suspension. Each mirror is suspended from a series of pendulums, 4 stages of pendulum nested within each other, the mirror hanging from the lowest stage by glass fibers finer than a human hair. A pendulum acts as a mechanical low-pass filter. Above its resonant frequency, it strongly attenuates vibrations transmitted from its mounting point. 4 stages of pendulum, each with a resonant frequency of approximately 1 Hz, provide attenuation of seismic noise by a factor of roughly 10 to the minus 40 above 10 Hz, reducing the seismic displacement of the mirrors to a level below the gravitational wave signal at the frequencies LIGO is designed to detect. The pendulum system itself sits on an actively controlled platform. Sensors measure the motion of the platform at low frequencies, and actuators apply corrective forces in real time, reducing the residual motion of the platform before the pendulums even begin their passive filtering. The combination of active control at low frequency and passive pendulum isolation at higher frequency gives the system the seismic isolation it needs to function. Thermal noise is a separate challenge. Every object at a temperature above absolute zero vibrates at the atomic level. This is the physical meaning of temperature. The mirror itself, the glass fibers suspending it, the pendulum stages above, all of them are vibrating randomly, driven by thermal energy. These vibrations displace the mirror surface by tiny amounts that are larger than the gravitational wave signal at some frequencies. The choice of materials, fused silica for the mirrors and suspension fibers, rather than metals or crystalline materials, is motivated in part by the low mechanical loss of fused silica. A material with low mechanical loss concentrates its thermal noise at narrow resonant frequencies, rather than spreading it broadly across the detection band, making it easier to avoid in the analysis. Laser noise is another source of contamination. The power of the laser must be extremely stable. Fluctuations in laser power produce fluctuations in the output of the interferometer that mimic a signal. The laser used in advanced LIGO produces approximately 200 watts of continuous wave infrared light at a wavelength of 1064 nanometers. This power is amplified and stabilized before entering the interferometer, and additional optical cavities, the power recycling cavity and the signal recycling cavity, are used to enhance the light stored in the arms while suppressing laser noise. And then there is quantum noise. At the most fundamental level, the sensitivity of any interferometer is limited by quantum mechanics. Light consists of photons, and photons arrive at the detector in a random stream. Even from a perfectly stable laser, the number of photons arriving per unit time fluctuates randomly. This statistical noise is called shot noise, and it limits how precisely the output of the interferometer can be measured at high frequencies. At low frequencies, a different quantum effect dominates. The radiation pressure of the photons pushes on the mirror surfaces and causes random displacements. This is called radiation pressure noise, or quantum back action. Together, shot noise and radiation pressure noise form the standard quantum limit for interferometric measurement. Advanced LIGO partially circumvents this limit using a technique called squeezed light injection, injecting quantum mechanically manipulated light into the output port of the interferometer that reduces shot noise at the cost of increasing radiation pressure noise in a frequency band where radiation pressure is less limiting. This technique, which would have seemed like science fiction to the first generation of LIGO researchers, is now a standard operational tool at the detector. You are still standing inside the tube. Outside the sealed vacuum enclosure, the Louisiana Bayou moves at its own rhythm. Alligators in the drainage channels, herons standing still in the shallow water. Trucks on Louisiana Highway 190, 5 kilometers to the north, carrying goods between Baton Rouge and Hammond. Every one of those trucks sends a seismic disturbance through the ground. Every train that passes within 10 kilometers registers in the data stream. The ocean waves on the Gulf of Mexico, 150 kilometers to the south, generate microseismic noise that arrives continuously, 24 hours a day. The machine feels all of it. The seismic isolation system suppresses all of it below the level that would contaminate the gravitational wave band. But the data is never perfectly clean. Scattered light, laser light that leaks out of the main beam path and finds its way back in after reflecting off a surface, can produce narrow noise features. Electromagnetic interference from electrical equipment can produce noise. The control systems themselves, which apply forces to the mirrors to keep them aligned and at resonance, inject small amounts of noise through the actuators. The people who built this machine spent 40 years learning how to find and suppress every one of these noise sources. The history of LIGO is inseparable from the history of this noise hunting. The decades of incremental improvements, failed designs, rebuilt components, arguments about which noise sources were tractable and which were fundamental. The original LIGO detectors, built in the early 2000s, were never sensitive enough to plausibly detect gravitational waves from known astrophysical sources. This was understood going in. The original detectors were a proof of concept, a demonstration that the infrastructure could be built, the noise could be controlled to a level approaching the required sensitivity, and the operation of kilometer-scale interferometers was feasible. They ran from 2002 to 2010, collecting data, setting upper limits, and finding no confirmed detections. Then they were shut down for 5 years. The upgrade to advanced LIGO was a comprehensive redesign of almost every subsystem. Higher laser power, improved seismic isolation. The multi-stage pendulum system replaced the simpler single-stage suspension of initial LIGO. Better mirror coatings, signal recycling, squeezed light. The goal was to improve sensitivity by a factor of 10 compared to initial LIGO, which corresponds to an increase in detectable volume of space by a factor of 1,000, since volume scales as the cube of distance. A factor of 10 improvement in strain sensitivity means a factor of 1,000 more binary mergers within the detectable range. Advanced LIGO installation completed in 2014. Engineering runs and commissioning, testing the upgraded systems, identifying new noise sources, optimizing performance, continued into 2015. The first formal observing run, designated 01, was scheduled to begin on September 18, 2015. On September 14, 2015, the detectors were in an engineering run. They were operating, collecting data, performing well above the sensitivity of initial LIGO, but not yet in official observing mode. No one had scheduled a detection for this morning. At 9 hours 50 minutes and 45 seconds UTC, the Livingston detector registered the signal. The Automated Data Analysis Pipeline, a system called CWB, Coherent Wave Burst, processed the data in near real time, looking for coherent transient signals in both detectors simultaneously. At approximately noon local time in Germany, a graduate student named Marco Drago, who was monitoring the automated pipeline output remotely from the Albert Einstein Institute in Hanover, noticed an event that the algorithm had flagged. He looked at the waveform. It was a chirp. Not a noise artifact, not a glitch, not a corrupted data segment. The shape of the signal, the smooth frequency sweep from low to high, the peak amplitude at merger, the rapid decay of the ring down, matched almost exactly the theoretical template for a binary black hole merger. It was present in both detectors. The Hanford signal arrived 7 milliseconds after Livingston, consistent with a source direction in the southern sky, and the travel time for a signal moving at light speed between the two detector sites. Drago sent an email. The LIGO scientific collaboration has a protocol for candidate events. The email initiated a chain of notifications to team leads, to data quality experts, to analysts specializing in parameter estimation and waveform comparison. Within hours, the core collaboration knew that something had happened. Within days, the preliminary analysis confirmed that the signal was consistent with a binary black hole merger at a distance of approximately 410 megaparsecs, roughly the distance light travels in 1 1/3 billion years. And then the silence began. Because LIGO had a policy, throughout the initial and advanced LIGO era, the collaboration had conducted occasional blind injection exercises, deliberate, secret insertions of fake signals into the data stream by a small team with the authority and technical access to do so. The purpose was to test the full pipeline: detection, analysis, vetting, and announcement. A blind injection would look exactly like a real event in the data. Only the 4 people with injection authority knew whether any given candidate was real or fake. When GW150914 was detected, the collaboration did not know if it was a blind injection. They had to verify. They had to eliminate every plausible non-gravitational wave explanation for the signal. They had to confirm that both detectors were functioning normally at the time of the event, that no known environmental disturbance had simultaneously affected both sites, that the waveform was consistent across independent analysis methods, and that the statistical significance of the detection was sufficient. Less than one event of this apparent strength expected from noise alone in the entire history of LIGO operation to that point. The statistical significance, when fully computed, was 5.1 sigma. In particle physics convention, 5 sigma is the threshold for claiming a discovery. The probability of a noise fluctuation producing an event this significant was approximately 1 in 3.5 million. This calculation was performed by analyzing months of data from both detectors before the event, characterizing the noise background, and determining how often random coincidences between the two detectors could produce an event resembling GW150914. 1 in 3.5 million. And then the injection team confirmed there had been no blind injection in progress on September 14th, 2015. The signal was real. The verification process took 5 months, From mid-September 2015 to February 11, 2016, the collaboration, roughly 1,000 scientists across dozens of institutions on multiple continents, worked under a strict information embargo. The detection was not announced publicly. Papers were written, reviewed internally, submitted to physical review letters, under confidentiality, reviewed by external referees who also kept the secret. 1,000 people knew. The world did not. On February 11, 2016, at a simultaneous press conference in Washington, the 600th in locations around the world, LIGO Executive Director David Reitze stood at a podium and said, "We have detected gravitational waves. We did it." The room responded in a way that rooms rarely respond to scientific announcements. The papers were published that same day in physical review letters. The title of the primary detection paper was simply "Observation of Gravitational Waves from a Binary Black Hole Merger." It was authored by the LIGO Scientific Collaboration and the Virgo Collaboration. Over 1,000 authors, a list that required multiple pages. Within days, the paper had accumulated more citations than almost any physics paper in recent memory. In 2017, the Nobel Prize in Physics was awarded to Rainer Weiss, Barry Barish, and Kip Thorne for decisive contributions to the LIGO detector and the observation of gravitational waves. Weiss had proposed the interferometric detection concept in a 1972 MIT internal report, 43 years before the detection. The report was never published in a journal. It was an internal MIT document written as a teaching exercise in which Weiss worked through the physics of an interferometric gravitational wave detector from first principles, the noise sources, the sensitivity limits, the basic optical configuration. He estimated what sensitivity would be required to detect waves from known astrophysical sources. His estimates were roughly correct. The document laid out in 1972 the path that would lead to September 2015. It then took funding. It took 3 decades of sustained support from the National Science Foundation, the primary funder of LIGO throughout its construction and operation. It took the organizational skill of Barry Barish, who restructured the LIGO scientific collaboration in the 1990s into a form capable of managing a project of this complexity and scale. It took the theoretical groundwork of Kip Thorne and his students and collaborators, who developed the waveform predictions, the templates of what a binary merger signal should look like in the detector, without which matched filtering would have been impossible. Without knowing what shape to look for, the detection of GW 150914 might have been dismissed as a glitch even when the signal was present. Every element of the chain mattered. The outside of the LIGO building in Livingston is not remarkable. A low concrete and steel structure surrounded by flat landscape and drainage channels, a gravel parking lot, a chain link fence. Inside the control room, banks of monitors display the current state of the interferometer in real time, noise floor, alignment, output power, servo control signals. During a science run, operators monitor the system around the clock, responding to disturbances, maintaining lock, the condition in which the laser cavities are held at resonance and the interferometer is sensitive to gravitational waves. The machine requires constant attention. Earthquakes anywhere in the world above a certain magnitude will break the lock. A truck driving too close to the access road can break the lock. The control system must continuously apply tiny corrective forces to every mirror to counteract thermal drift, seismic motion, and the slow relaxation of mechanical components. The operators who maintain the lock are not physicists solving equations. They are skilled technicians who understand the machine the way a surgeon understands anatomy, intuitively, practically, with the knowledge that comes only from hours of direct contact with the system. You are leaving the tube now. You step out of the vacuum enclosure, through the airlock into the humid Louisiana air. The sun is rising over the flat landscape to the east. The bayou is quiet. Somewhere above you, a gravitational wave is passing through the atmosphere, through your body, through the ground, through the building you just left. The machine inside is waiting for the next one. It will not wait long. The data produced by advanced LIGO is not a simple record of arm-length differences over time. It is a continuous, complex time series sampled at 16,384 points per second, each second of operation producing more than 16,000 individual measurements of the interferometer output. The data from both detectors is recorded simultaneously, along with thousands of auxiliary channels monitoring environmental conditions, seismic accelerometers, magnetometers, microphones, temperature sensors, laser power monitors, and the outputs of hundreds of servo control systems. The main gravitational wave channel, the strain channel, H of T, contains the signal. It also contains noise from every source that the isolation and control systems have not perfectly suppressed. The job of data analysis is to extract real astrophysical signals from this noise, to set limits on how loud a signal would need to be detectable, or to characterize the noise itself well enough that future detections can be interpreted correctly. The noise in the strain channel is not random in the simple sense. It has structure. There are narrow spectral lines at specific frequencies, caused by the resonances of mechanical components, by the electrical power grid at 60 Hz and its harmonics, by the calibration system that injects known signals to verify the instrument's response. There are broadband noise features caused by thermal motion in the mirrors and suspensions, and there are transient events, glitches, caused by scattered light, by sudden releases of stress in mechanical components, by nearby seismic events. Glitches are a persistent challenge. They can resemble astrophysical signals, particularly short-duration events like the merger of two black holes. They occur at both detector sites, sometimes simultaneously by coincidence. Distinguishing a glitch from a real signal requires examining the data quality at the time of the event, checking whether the event is consistent with the frequency-dependent sensitivity of the instrument, verifying that no known environmental disturbance occurred at the right time, and comparing the morphology of the candidate against the catalog of known glitch types. The collaboration maintains a detailed glitch taxonomy, a catalog of known noise sources and their signatures in the strain channel, accumulated over years of operation. GW150914 resembled no known noise source. Its waveform was consistent with a compact binary merger and inconsistent with every category of glitch in the database. In the first 3 observing runs, LIGO and Virgo detected more than 90 confirmed gravitational wave events. The universe, it turns out, is full of binary mergers, black holes colliding, neutron stars spiraling together. Events that were invisible to every telescope ever built are now routinely cataloged, measured, and analyzed. The chirp that arrived on September 14, 2015, was not a rare exception. It was the first word of a language the universe had been speaking all along. You are moving backward in time now. Not literally, time does not run backward, and the causal structure of spacetime forbids it, but in the way that science reconstructs the past from present evidence, you are moving back along the signal, back along the full distance of travel. Back through the in-spiral and merger and ring down, back to the moment before the chirp, to the moment just before 9 hours 50 minutes and 45 seconds UTC on September 14th, 2015, when the signal had not yet arrived, when the history of astronomy was intact and the universe was still something humans could only see. It is the morning of September 14th, 2015. In Livingston, Louisiana, the LIGO detector is running in engineering mode. The lock has been maintained through the night. The noise floor is close to design sensitivity. The advanced LIGO upgrade has succeeded in improving sensitivity by approximately a factor of 3 compared to initial LIGO in the most critical frequency band, and work continues to push the performance further. In the control room, the overnight operators are completing their shift. The automated pipeline is processing data continuously. In Hanford, Washington, the situation is similar. The second detector is locked, operating, recording. The night shift at Hanford would have watched the same quiet data stream, noise floor plots, control signal monitors, routine checks of the optical alignment. At universities and research institutes across the United States, Europe, and Australia, members of the LIGO scientific collaboration are sleeping, working, eating breakfast. Most are not watching the data in real time. The pipeline is automated. Human review of candidate events happens after the pipeline flags them. In Hanover, Germany, it is mid-afternoon. Marco Drago, a postdoctoral researcher at the Albert Einstein Institute, is monitoring automated pipeline output as part of his duties. He is 29 years old. He has worked on LIGO data analysis for years and has seen many noise glitches flagged by the algorithm, terrestrial disturbances that the system mistakenly identifies as candidate events, distinguished from real signals only by careful examination of data quality and environmental monitors. He sees the flag for GW150914 at approximately 11:54 a.m. local time. He looks at the waveform in the Livingston data. He looks at the waveform in the Hanford data. The two waveforms, separated by 7 milliseconds, are nearly identical. The characteristic shape, the slow rise, the sharp sweep, the sudden truncation at merger, is exactly what general relativity predicts for a binary black hole in spiral. He sends a message to colleagues. I think we have something. He is right. What he is looking at has traveled 1.3 billion light years. It was produced when the most complex life on Earth was single-celled. It has passed through the full age of vertebrate evolution, through the rise and fall of every geological period, through the emergence of human consciousness and the entirety of recorded history, without once being slowed or scattered or absorbed. And it ended its journey in a data file on a computer server in Louisiana. The process of confirming the detection is meticulous. Data quality checks examine every environmental monitor in the vicinity of both detectors, magnetometers, accelerometers, microphones, radio frequency monitors, looking for any physical disturbance that could have produced a false signal. None are found. The signal passes every data quality check applied to it. Independent analysis pipelines, algorithms with different assumptions and different approaches to signal extraction all find the same event at the same time with the same parameters. The consistency across methods is a powerful argument against a false signal, because different analysis pipelines have different systematic biases and noise sensitivities. A noise artifact would almost certainly manifest differently in different pipelines. Parameter estimation, the process of inferring the physical properties of the source from the waveform, is performed using Bayesian inference, a large set of theoretical waveform templates computed from numerical relativity simulations and analytical approximations is compared to the data. The posterior probability distributions for the source parameters, the component masses, the final mass, the distance, the sky location, the spin magnitudes and orientations, are computed and reported with uncertainties. The results are consistent. Two black holes, masses approximately 36 and 29 solar masses, merging at a distance of approximately 410 megaparsecs, in a region of the southern sky spanning several hundred square degrees. The source cannot be localized precisely with only two detectors. A precise sky localization requires the timing information from 3 or more detectors. With 2 detectors and the 7 millisecond delay, the source is constrained to a band across the sky consistent with that time delay, but not to a specific point. The waveform is tested against general relativity directly. The observed chirp mass, a combination of the two component masses that is most precisely determined from the in-spiral phase of the waveform, matches the value inferred from the merger and ring-down phases. The ring-down frequencies and decay times are consistent with a final Kerr black hole of 62 solar masses and a spin of approximately 0.67 times the maximum. General relativity makes specific predictions for the relationship between these quantities, and the observations are consistent with those predictions at the level of measurement precision available. This is not just a detection, it is a test of general relativity in the strong field, highly dynamic regime, conditions that no previous experiment had ever accessed. Previous tests of general relativity, Mercury's perihelion precession, the deflection of starlight by the sun, the Shapiro delay, the Hulse-Taylor binary pulsar, all probed gravity in conditions where the fields were weak and the motion was slow compared to light speed. GW 150914 came from a system where the gravitational fields were extreme and the velocities were relativistic. The agreement with general relativity in this regime is a profound confirmation of the theory's validity in conditions far beyond its original tests. The month passes, then another month. The collaboration continues verifying, more noise checks, more parameter estimation runs. Reviewing the data for the same period without the signal present, to characterize the background, writing the analysis papers, not just the main detection paper but the companion papers, the source properties paper, the tests of general relativity paper, the detector characterization paper, the astrophysical implications paper. Each paper is internally reviewed by hundreds of collaboration members. Each goes through multiple rounds of comment and revision before the collaboration approves it for submission. The editorial process at Physical Review Letters, conducted under strict confidentiality, takes additional weeks. The embargo holds. In December 2015, at a scientific conference, a rumor circulates. Someone has heard something from someone who heard something else. The New York Times publishes a brief item noting that LIGO researchers seem unusually excited at conferences. The collaboration says nothing formally. The papers are not yet published. In January 2016, The papers are accepted by physical review letters. The announcement date is set February 11th, 2016. You are in Washington, the 600th on that morning. The press conference is at the National Press Club. Rainer Weiss sits on the stage, white-haired, 83 years old, having spent more than 40 years of his career working toward this moment. Beside him, Kip Thorne and Barry Barish. In the audience, journalists, scientists, government officials. The formal presentations begin. The background of the project is described, the history of the detector, the science of gravitational waves, then the result. David Wrightsey steps to the microphone. He pauses. We have detected gravitational waves. We did it. The room responds before the next sentence begins. Outside the press club, on the streets of Washington the 600th, traffic moves. People walk past on their way to work or to coffee or to appointments. Almost none of them know what has just been announced. The discovery that will reshape gravitational astrophysics, that will open an entirely new observational window on the universe, that will eventually lead to a Nobel Prize, is happening in a room that most of the city is unaware of. The universe does not pause for announcements. The gravitational waves from GW 150914 are 8 light-years beyond Earth now, beyond Sirius, the brightest star in the night sky, moving outward. Other gravitational waves from sources detected in the years since, from the 90-plus events cataloged in the first 3 observing runs, are also propagating outward from Earth in every direction, carrying the record of our detection in the patterns of our own radio emissions, our own laser light, our own computational processes. We are now a source of electromagnetic signals for any civilization distant enough to receive them. We are also, for the first time, receivers of gravitational signals. The night is deep now. The events of that September morning, the Louisiana Bayou in the early hours, the data pipeline running unattended, the graduate student in Hanover seeing a chirp on a screen, are fixed in the past, immutable, as real as the space-time geometry that carried the signal across the breadth of the observable universe. Your breathing is slower than it was. The details are settling, not disappearing, but softening. The chirp mass, the ring-down frequencies. The 7 milliseconds between detectors, the 5.1 sigma confidence, the 5 months of silence, the moment at the microphone. They are all real. They happened. The universe produced an event over 1 billion years ago, and in 2015, human beings on a planet orbiting an unremarkable star in an outer spiral arm of a middling galaxy built an instrument precise enough to detect it. The mirrors are still hanging in Louisiana and Washington tonight. The laser is still bouncing. The control systems are still holding lock. The machine is listening. Let the weight of the day settle. Let the specific details go soft at the edges. The science underneath them does not go anywhere. The geometry of space-time that made the detection possible is the same geometry that holds you in place right now, that gives you weight, that curves the path of every photon passing through the atmosphere above you, that causes time to pass for you at the particular rate it does, slightly slower than it would in open space. You are resting inside a universe that speaks in the language of bent space. The machine heard it once. It has heard it 90 more times since. It is listening right now, tonight, for the next one. Rest now. The signal from GW150914 is still traveling. It will travel until the universe is cold. There is no friction to slow it, no medium to absorb it, just the geometry of spacetime, propagating its own disturbance outward at the speed of light forever. That is something to carry into sleep. Not urgency, not complexity, just the quiet fact of a universe that has been communicating for 13.8 billion years, and the fact that we are right now in the first generation that is learning to listen. Sleep is very close. Let it come. The machine is awake, so you do not have to be. Before September 14th, 2015, every piece of information humanity had ever gathered about the universe arrived in the same form. Light. Not always visible light. Radio waves, X-rays, gamma rays, infrared, ultraviolet, microwave. But all of it electromagnetic radiation. All of it the same fundamental phenomenon, oscillating electric and magnetic fields, propagating through space at 300 million meters per second. For the entire history of astronomy, from the first human being who looked up and wondered what the bright points in the night sky were, to the construction of the Hubble Space Telescope, to the launch of the Fermi Gamma Ray Space Telescope, to the operation of the Atacama Large Millimeter Array in the Chilean desert, every observation was a measurement of electromagnetic radiation. This is not a limitation of imagination or technology. It is a limitation of what the universe made available to us. The cosmos is transparent to light across much of the electromagnetic spectrum. Light travels freely through intergalactic space. It carries information from distant sources and delivers that information to our instruments. For most of the universe, most of the time, light is an adequate messenger. But not everywhere, and not always. There are regions of the universe from which no light escapes at all. The interiors of black holes, the regions inside the event horizon, are permanently hidden from electromagnetic observation, not because we lack the right telescope, because the causal structure of spacetime inside the event horizon is such that no signal of any electromagnetic kind can propagate outward. The curvature is too extreme. Light paths curve back inward before they can reach the outside. Gravitational waves are different. They are not light. They are not electromagnetic radiation. They do not originate from charged particles. They originate from mass in motion, from the acceleration of mass energy in any form, and they are not blocked by the event horizon, a gravitational wave produced by the dynamics of a merging black hole system propagates outward freely, carrying direct information about the masses, spins, and orbital dynamics of the objects involved. Information that no electromagnetic signal could carry because no electromagnetic signal was produced in the merger of GW150914. Two black holes merged 1.3 billion light-years away. There was no flash, no gamma-ray burst, no X-ray afterglow, no radio emission, no visible light whatsoever. The only signal was the gravitational wave, and we caught it. You are somewhere quiet now. The sounds of the day have receded. Whatever the room around you contains, furniture, walls, the ordinary geometry of a human dwelling, it is all very still. Your body is horizontal or close to it. The weight of your limbs has settled into whatever surface supports you. The universe outside continues exactly as it would if you were awake and moving. Gravitational waves are passing through the building. The Earth's gravity is curving space-time around you. Light from distant galaxies is arriving at the upper atmosphere and being absorbed or reflected without anyone watching it. Somewhere in the Milky Way, a neutron star is rotating 40 times per second, and its slight asymmetry is causing it to emit a continuous gravitational wave at 80 Hz. A frequency in the middle of the range LIGO is designed to detect. That wave has been propagating outwards since the neutron star formed, centuries or millennia ago, and it is moving through the solar system right now. LIGO may be listening to it, or it may be below the current sensitivity threshold, waiting for the next detector upgrade to bring it into view. This is the nature of the new window that opened in 2015. It is not complete. It is not all-seeing. It is a first aperture, narrow, limited in frequency range, limited in sensitivity, but real. And through it, in the years since that September morning, the universe has been remarkably forthcoming. By the end of the third LIGO Virgo observing run in 2021, the Gravitational Wave Transient Catalog, GWTC-3, contained 90 confirmed events, 90 binary mergers detected in gravitational waves. The overwhelming majority were binary black hole mergers, systems similar to GW150914, with component masses ranging from a few solar masses to more than 100. A smaller number involved neutron stars. The distribution of detected black hole masses has already produced surprises. Several detected events involve black holes in the range of roughly 40 to 100 solar masses, a range that stellar evolution theory suggests should be difficult to produce directly from a single stellar collapse. Stars in the mass range that would produce these black holes are expected to undergo a process called pair instability, a runaway production of electron-positron pairs in the stellar core that destabilizes the star and causes it to explode completely, leaving no compact remnant. If this theoretical prediction is correct, black holes in this mass range, the pair instability mass gap, should be rare or absent. They are not absent in the LIGO catalog. This suggests that some of the detected black holes may be the products of previous mergers, black holes that formed from the merger of two smaller black holes, grew in mass, and then merged again with another companion. If this hierarchical merger scenario is correct, it implies that black holes can undergo chains of mergers in dense stellar environments, globular clusters, galactic nuclei, building up mass over multiple generations. The Gravitational Wave Catalog is providing the first direct census of the black hole population in the nearby universe, and that census is already challenging the existing theoretical picture. But the most scientifically important event in the catalog, after GW150914, was not a black hole merger. It was the collision of two neutron stars. On August 17, 2017, at 12 hours 41 minutes and 4 seconds UTC, the LIGO detectors in Livingston and Hanford, and the Virgo detector in Cassina, Italy, which had joined the network 2 weeks earlier, recorded a gravitational wave signal designated GW170817. The signal was different from the black hole events. It was longer, nearly 100 seconds in the detector band, compared to the fraction of a second for GW150914. It was higher in frequency at merger, and the component masses, approximately 1.17 and 1.60 solar masses, were consistent with neutron stars rather than black holes. 1.7 seconds after the gravitational wave signal ended, The Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same region of the sky. GW 170817 and its gamma ray counterpart arrived from a distance of approximately 40 megaparsecs, 40 million parsecs, roughly 130 million light-years, from a galaxy called NGC 4993 in the constellation Hydra. The 1.7-second delay between the gravitational wave and the gamma ray after 130 million years of travel placed an extraordinarily tight constraint on the difference in speed between gravitational waves and light, less than 1 part in 10 to the 15th. They travel at the same speed, to 15 decimal places of precision. This was the beginning of multi-messenger gravitational wave astronomy. Within hours of the GW 170817 detection, observatories around the world were pointed at NGC 4993. The source was visible in optical light, a faint blue point that brightened and then reddened over the following days. This was the kilonova, the optical and infrared transient produced by the radioactive decay of heavy elements, synthesized in the neutron-rich debris ejected by the merger. The kilonova of GW 170817 was observed across the electromagnetic spectrum, radio, optical, infrared, X-ray, by dozens of independent telescopes on 6 continents and in space. The heavy elements created in this event were directly identified through spectroscopy. Strontium was confirmed, and critically, the observations were consistent with the production of process elements, the rapid neutron capture process that builds elements heavier than iron in environments of extreme neutron density. Gold? Platinum? The origin of these elements had been debated for decades. Core collapse supernovae were candidates. Neutron star mergers were candidates. GW 170817 provided the first direct observational confirmation that neutron star mergers are a site of heavy element production, that the gold in any ring, the platinum in any catalytic converter, the iodine in every living body, was forged in events exactly like this one, in the final moments of 2 neutron stars spiraling together. You are made of elements that came from collisions like GW 170817. Not metaphorically, but it is worth pausing on what that phrase actually means in physical terms, because the connection between the kilonova and your body is not poetic license. It is nucleosynthesis, the sequence of nuclear reactions by which the elements in your body were assembled from lighter elements in specific astrophysical environments. The lightest elements, hydrogen and helium, were produced in the first 3 minutes after the Big Bang in the hot, dense plasma of the early universe, before any stars existed. The carbon, nitrogen, and oxygen that constitute the majority of your body's mass were produced in the cores of stars similar to the Sun through helium fusion reactions, and were scattered into space when those stars died. The iron in your blood was produced in the cores of massive stars, the same kind of stars that produced the black holes of GW 150914 during the final stages of stellar evolution, and scattered in supernova explosions. But the heaviest elements, those heavier than iron and beyond the reach of stellar fusion, require a different, more violent environment. They are produced by the reprocess, rapid neutron capture, in which atomic nuclei are bombarded by neutrons at such a rate that they absorb multiple neutrons before they have time to decay, building up into heavy, neutron-rich nuclei that subsequently beta decay into stable heavy elements. The reprocess requires conditions of extreme neutron density, conditions that exist for brief moments in neutron star mergers. The kilonova of GW 170817 confirmed this directly. Spectroscopic observations of the optical transient identified absorption and emission features consistent with heavy process elements. Strontium was identified conclusively. The observations were also consistent with significant production of lanthanides, the row of elements on the periodic table from lanthanum to lutetium, which have the high opacities that cause the kilonova to redden over time as the blue optical emission fades, and infrared emission from AIDS and infrared emission from AIDS. Lanthanide-rich ejecta takes over. The amount of gold estimated to have been produced in GW 170817 alone was several times the mass of the Earth. This gold is now dispersed in the interstellar medium of NGC 4993, mixed with the gas and dust of the galaxy, available to be incorporated into future generations of stars and their planetary systems over the next billions of years. The universe manufactures heavy elements in violence and scatters them quietly into the spaces between stars, literally. The iron in your blood, the calcium in your bones, the oxygen in every breath, all of it was produced in stellar interiors and stellar explosions. In some fraction of the heavier elements in your body, the iodine, the barium, the trace quantities of gold that exist in human tissue at parts per billion concentrations, was produced in neutron star mergers in events like the one LIGO detected on August 17, 2017. The kilonova of GW 170817 ejected an estimated mass of heavy process elements equivalent to several percent of a solar mass, hundreds of Earth masses of gold, platinum, and other heavy elements scattered into the interstellar medium of NGC 4993, where it will eventually be incorporated into new stars and new planetary systems. The universe manufactures heavy elements in violence and scatters them into the quiet spaces between stars. Some of what it scattered found its way to Earth. Some of it is in your body right now. Let that settle. The network of gravitational wave detectors has continued to grow since 2017. The Virgo detector in Italy achieved operating sensitivity in time to participate in the detection of GW 170817, contributing the third data point needed to triangulate the source location to a region small enough for optical telescopes to search efficiently. Kagra, a gravitational wave detector in Japan, built underground in the Kamioka mine to reduce seismic noise, joined the network in 2020 and has participated in subsequent observing runs. LIGO India, currently under construction, will add a fourth detector site to the global network, further improving sky localization and increasing the detection rate. But the most significant expansions of gravitational wave astronomy in the coming decades will come from detectors operating at frequencies that ground-based instruments cannot access. The reason is straightforward. Ground-based interferometers like LIGO are limited at low frequencies by seismic noise. No matter how sophisticated the isolation system, the motion of the Earth's surface, driven by ocean waves, atmospheric pressure, and human activity, sets a practical lower limit on the frequencies that can be observed. Below approximately 10 Hz, ground-based detectors are effectively blind. But some of the most scientifically interesting gravitational wave sources radiate at frequencies far below 10 Hz. Supermassive black hole binaries, systems with component masses of millions to billions of solar masses, radiate gravitational waves at millihertz frequencies as they inspiral. The merger of supermassive black holes, which occurs when two galaxies collide and their central black holes eventually sink to the center of the merged galaxy and spiral together, would produce a gravitational wave signal orders of magnitude stronger than any stellar mass binary merger. But the signal would be at frequencies between roughly 10 to the -4 and 10 to the -1 hertz, completely inaccessible from the ground. This is why the Laser Interferometer Space Antenna, LISA, is being built. LISA is a space-based gravitational wave detector, a mission of the European Space Agency with NASA participation, currently scheduled for launch in the mid-2030s. It consists of 3 spacecraft flying in a triangular formation, separated from each other by 2.5 million kilometers, 2.5 million kilometers, roughly 6 times the distance from the Earth to the Moon. Laser interferometry between the 3 spacecraft will measure the distance between them to a precision sufficient to detect the space-time distortions produced by gravitational waves in the millihertz band. At this frequency, LISA will detect supermassive black hole mergers across the entire observable universe. It will detect thousands of compact binary systems within our own galaxy, white dwarf pairs, neutron star pairs, black hole pairs, whose signals have been building up in the millihertz band for millions of years and are still far from merger. It will also detect the inspiral phase of systems like GW 150914 months or years before they enter the LIGO band, giving advance warning to ground-based detectors, which can then be oriented and prepared for the merger signal. LISA will see the universe in a frequency band that has never been observed before, ever, by any instrument. But even LISA has a low frequency limit. At nanohertz frequencies, billionths of a hertz, corresponding to gravitational wave periods of years to decades, a completely different detection method is required, and it already exists. Pulsar timing arrays use millisecond pulsars, rapidly rotating neutron stars that emit radio pulses with the regularity of atomic clocks, as the endpoints of a galaxy-scale gravitational wave detector. If a gravitational wave passes between a pulsar and the Earth, it distorts the spacetime the radio pulses travel through, causing the pulses to arrive slightly early or slightly late. By monitoring an array of millisecond pulsars distributed across the sky and looking for correlated timing residuals, patterns in the early and late arrivals that match the expected signature of gravitational waves, it is possible to detect gravitational waves at nanohertz frequencies. The characteristic signature of a gravitational wave background in pulsar timing data is called the Hellingsdowns curve, a specific pattern of correlations between pairs of pulsars as a function of the angle between them in the sky. The detection of this correlation is what distinguishes a true gravitational wave background from correlated noise sources affecting multiple pulsars simultaneously. In June 2023, 4 independent pulsar timing array collaborations, Nanograv in North America, the European Pulsar Timing Array, the Parkas Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array, simultaneously published results showing strong evidence for a gravitational wave background at nanohertz frequencies, with correlation patterns consistent with the Hellingsdowns signature. The most likely source of this background is the superposition of gravitational waves from millions of supermassive black hole binary systems throughout the universe, systems at various stages of inspiral, too distant and too numerous to be detected individually, but collectively producing a stochastic background that pervades the universe at nanohertz frequencies. This is the gravitational wave background hum of the universe. It is present right now. It has been present for the entire history of humanity, for the entire history of life on Earth, and we had no way to hear it until millisecond pulsars gave us ears sensitive enough to the right frequency range. The universe has been broadcasting at multiple frequencies simultaneously for billions of years. We are learning, one band at a time, how to listen. And beyond all of this, beyond the stellar mass mergers that LIGO detects, beyond the supermassive black hole mergers that LISA will detect, beyond the nanohertz background that pulsar timing arrays are now beginning to characterize, there is a frequency band that no current or planned instrument can reach. It is the gravitational wave signal from the first fractions of a second after the Big Bang. The very early universe was not smooth. In the first moments after the Big Bang, in fractions of a second so small they are difficult to express in ordinary language, the universe underwent phase transitions, rapid changes in the structure of fundamental fields that would have produced gravitational waves across an enormous range of frequencies. If the universe underwent inflation, the period of exponential expansion that cosmologists believe occurred in the first 10 to the negative 32nd seconds, the quantum fluctuations of the gravitational field during inflation would have been stretched to macroscopic scales and frozen in as a background of primordial gravitational waves. This primordial background, if it exists, is currently at frequencies too low even for pulsar timing arrays. It may be detectable through its imprint on the polarization of the cosmic microwave background radiation, the faint afterglow of the Big Bang that we can observe at microwave frequencies across the entire sky. Experiments designed to detect this B-mode polarization signal, the Simons Observatory in Chile, the CMBS-4 experiment, and future space missions are searching for this signature right now. If detected, it would be a gravitational wave signal from the first instant of the universe, from a moment before any matter in the standard sense existed, before the fundamental particles had acquired their masses, before the forces of nature had separated into their current distinct forms. It would be a direct observation of the earliest moment in the history of the cosmos that physics currently knows how to describe. Your breathing is very slow now. The room is very still. These things, the nanohertz background, the LISA millihertz band, the primordial signal hiding in the polarization of the microwave sky, they are not speculation. They are predictions grounded in the same physics that predicted GW 150914 before anyone had ever detected a gravitational wave. The physics of general relativity and quantum field theory has been confirmed by so many independent experiments in so many independent ways that the predictions it makes for gravitational wave signals across all frequency bands carry a weight that goes beyond theoretical possibility. They are almost certainly real. We have not yet built the instruments to hear all of them, but we know they are there. This is the position of science in the autumn of 2015, the summer of 2023, and every moment between and after, standing at the edge of what the instruments can reach, knowing with confidence that there is more beyond that edge, and building the tools to hear it. The chirp of GW 150914 was not a conclusion. It was the first word. In the same way that Galileo's first telescope, a tube with two lenses, producing a magnification of roughly 30 times, opened a door that eventually led to the Hubble Space Telescope and the James Webb Space Telescope. The first detection of a gravitational wave has opened a door. The room behind that door contains the full gravitational wave universe, every black hole merger across cosmic time, every neutron star collision, every supermassive black hole binary at the center of every merging galaxy, and at the very back, barely visible, the gravitational signal from the first instant of the universe itself. We have the key. We opened the door on September 14th, 2015 at 9 hours 50 minutes and 45 seconds UTC. What is inside will take generations to fully explore. You are part of the generation that opened it. Not because you built the machine, or wrote the equations, or monitored the data pipeline, but because you are alive now in this particular window of history when the universe became audible for the first time. Every generation before yours, every human being who ever looked at the sky and asked what was out there, lived in a universe that was speaking and could not be heard. The gravitational signal from that distant merger passed through every one of their bodies, exactly as it passes through yours. They had no way to know it. You do. That is not a small thing. It is, in the longest possible view, one of the genuinely rare thresholds in the history of our species, comparable to the first use of lenses to magnify the sky, the first use of spectroscopy to determine the chemical composition of stars, the first detection of radio waves from space. Each of these moments opened a new channel between the universe and human understanding. Each of them changed what questions it was possible to ask. Gravitational wave astronomy is one of those moments. It happened in your lifetime. The machine in Louisiana is still running tonight. The mirrors are still hanging from their glass fiber suspensions, isolated from the seismic noise of the bayou by 4 stages of pendulum and active control. The laser is still bouncing. The control room operators are still watching the monitors. The automated pipeline is still processing data in near real time, looking for the characteristic chirp shape that signals a binary merger somewhere in the observable universe. The machine in Washington is still running. The machine in Italy is still running. In Japan, underground in the Kamioka mine, Kagra is listening. In India, the foundation is being laid for LIGO India. In the offices of space agencies in Europe and the United States, engineers are working on LISA, the spacecraft that will listen to the millihertz universe from a triangle of lasers 3 spacecraft wide, 2.5 million kilometers on each side, in orbit around the sun. In radio observatories across 4 continents, millisecond pulsars are being timed to nanosecond precision, and the data from all of them is being assembled into a picture of the nanohertz gravitational wave background that pervades the cosmos. The universe is being listened to, right now, at multiple frequencies simultaneously by instruments on the ground and in space, and distributed across the entire surface of the Earth. It has never been listened to this carefully before. The signals being collected right now will be analyzed for years. The catalog of detected events grows with each observing run, and each new event adds a data point to the population-level picture of binary black holes and neutron stars in the universe, their mass distribution, their spin properties, their merger rates per unit volume of space. These population statistics constrain the astrophysical processes that produce compact binaries, the initial mass function of stars, the physics of stellar evolution in binary systems, the fraction of massive stars that collapse to black holes versus neutron stars, the role of dense stellar environments in producing binary systems, the detection of gravitational waves from a binary with at least one object in the mass range between approximately 3 and 5 solar masses, the so-called mass gap between the heaviest known neutron stars and the lightest known black holes, has been reported in the GWTC catalog. The physical nature of mass gap objects is uncertain. They could be very massive neutron stars, low-mass black holes, or something else entirely. Gravitational wave observations are the most direct probe of this mass range available, because electromagnetic observations of compact objects in this mass range are extremely rare, and the objects themselves do not produce distinctive electromagnetic signatures simply by existing. The merger rate of binary black holes, inferred from the LIGO Virgo catalog, implies that within a distance of about 1 gigaparsec from Earth, 1 billion parsecs, binary black hole mergers occur at a rate of roughly 100 per year. The entire observable universe is billions of times larger in volume. The total rate of black hole mergers in the observable universe is therefore enormous, so large that the gravitational wave background from all of these unresolved mergers, too numerous and too distant to detect individually, contributes a stochastic signal in the LIGO band. Detecting this binary black hole background, distinct from the nanohertz background detected by pulsar timing arrays, is one of the science targets for future detector generations. And it is speaking. The night around you is very quiet. Your body is at rest. Your breathing is a slow, even rhythm. The thoughts that move through the mind at this hour, the ones that circle back, the ones that seem urgent at 2 in the morning and less so in daylight, they are becoming quieter. Not because they are resolved, because the scale of what surrounds them has shifted. 2 black holes collided 1.3 billion years ago. The signal they sent traveled for longer than complex life has existed on Earth. It arrived on a Tuesday morning in September in the Louisiana Bayou in a machine humans spent 40 years building because the physics said the signal should exist. And it did. Everything else that follows, the 90 detections after, the kilonova of GW170817 and its golden debris field, the nanohertz hum of 10,000 supermassive black hole pairs, the future measurement of LISA, the primordial whisper at the edge of the observable universe, all of it flows from that first Tuesday morning. The universe was always speaking. We finally learned to listen. Let the last details soften now. Let the specific numbers, the 5.1 sigma, the 410 megaparsecs, the 2.5 million kilometer arms of LISA, let them settle into the background where they belong. They will be there when you wake. The science does not disappear when you sleep. What stays, if anything stays, is simpler than the numbers. The universe is larger than you can hold in your mind at once. It has been operating for 13.8 billion years according to laws that do not bend to any preference. It produces events so violent they briefly outshine the combined light of every star in existence. It sends signals from those events across distances that make the human lifespan invisible, and in one small corner of one ordinary galaxy, On one unremarkable planet, a species of conscious beings built instruments sensitive enough to hear the geometry of space breathing, and they heard it. That is the story. That is the whole story. And you are resting inside it. Sleep well. If tonight brought the universe a little closer, if something in what you heard made the dark outside feel less empty and more full, please consider leaving a like or a comment and subscribing if you haven't already. Every episode is built on the same foundation: real science, real instruments, real events. The universe is stranger and deeper than any story invented from nothing, and there is always more to explore. Good night. The detectors are running. The universe continues. Everything you heard tonight is real. The signal is out there right now.